the Eridanus supervoid. You might have heard something about this gigantic cosmic void, a kind of a hole that may occupy a significant portion of the radius of the entire observable universe. This void may extend for 1 billion light-years, or even more. You may have watched videos or read articles about this supervoid. This structure is truly intriguing, even frightening. It's hard to imagine a piece of the universe where you can travel hundreds of millions of light-years and encounter almost nothing.
But here's the problem. It is quite possible that Eridanus supervoid does not exist.
Well, cosmic voids do exist, of course. For example, in the case of the local void, we know it exists because scientists have measured the speeds and distances to tens of thousands of galaxies located near the local group of galaxies and the Milky Way. This allows us to build a three-dimensional map of the distribution of galaxies in our part of the universe. Looking at this distribution, we can already see that galaxies form certain structures. They gather into clusters, while at the same time there are enormous voids, regions where there are far fewer galaxies than in clusters. And one of these voids is the local void. But the Eridanus supervoid hasn't been found in the same way. The possible existence of such an enormous void was suggested by indirect evidence, specifically by an anomaly in the cosmic microwave background radiation known as the cold spot. The existence of this spot is, to say the least, unexpected. That's precisely why it is considered an anomaly. And so the Eridanus supervoid is an attempt to theoretically explain the mechanism behind the formation of this anomaly. The thing is, a void of such an enormous size would itself be an anomaly.
So we're trying to get rid of one anomaly by using another anomaly.
Although voids have been found in the direction of the cold spot, the existence of such a supervoid is highly questionable, so we can't say it's confirmed. However, the cold spot itself does exist, and it's one of the most, if not the most peculiar and significant anomalies in the cosmic microwave background radiation, or CMB. Given how important the CMB is, it may call into question our current understanding of the structure and evolution of the universe. There are various attempts to explain this anomaly, ranging from the already mentioned supervoid to defects in space-time itself and even to the possibility of colliding universes.
We'll talk about all this and more. My name is Andrei, and this is Cosmos Elementary.
This weirdly-looking pattern is one of the main contemporary sources of our knowledge about the universe, the cosmic microwave background radiation, or CMB. I often talk about it in my videos precisely because it is so important. This is one of the pillars of the Big Bang theory. It provides us with information about the structure of the universe, its properties and evolution, as well as the distribution of matter and energy within it. Every time I touch on a topic in cosmology, it's practically impossible not to mention CMB, in one way or another. In my recent video about inflation, I talked about it quite a bit, and the cold spot is an anomaly that was found in observations of the CMB. To briefly remind you, for the first 380,000 years from what we commonly refer to as the beginning of the universe, before the first atoms could form, the universe was in a state of dense, hot and opaque plasma. And when it expanded and cooled enough to become transparent to radiation, photons were able to travel freely through the universe. Now we observe these photons from every direction in the sky as cosmic microwave background radiation. This is the earliest light of the universe that we can see, and it is sometimes referred to as the baby picture of the universe. Importantly, the conditions of the early universe are imprinted in this radiation, and by studying it we can gain a better understanding of the universe. At the moment the radiation appeared, it was in the visible range, but after billions of years of traveling through the expanding universe, it has shifted into the microwave part of the spectrum, and we observe it as microwaves. Many of you probably already know this, as well as the fact that modern measurements of the temperature of the cosmic microwave background radiation tell us that it is approximately 2.73 Kelvin. The temperature was much higher in the past. And if you're wondering how radiation can have a temperature, I discussed this in more detail in this video.
But to put it briefly, it is not just any radiation, it is thermal radiation.
Such radiation is emitted by matter with a temperature above absolute zero. It sounds like that should be any radiation, but that's not the case. Laser radiation is not thermal, nor is synchrotron radiation. Thermal radiation has its own characteristic spectrum, and from this spectrum, we can see that the properties of the radiation directly depend on the temperature of the matter. The colder a star is, the redder it appears, and the higher its temperature, the bluer it is. In general, not only do we know the current temperature of the CMB, but we are also interested in another property: its very high uniformity. On one hand, this is predicted by the Big Bang Theory, and on the other hand, it can also pose a problem that is addressed by inflation. Check out my recent video about it. The modern standard cosmological model states that the universe should be homogeneous, meaning it should be roughly the same everywhere on large enough scales, and isotropic, meaning that there shouldn't be any preferred direction. In other words, no matter where we look, it should be the same in all directions. Overall, many modern theories confirm this. Yes, of course, on smaller scales the universe has some structure, with some areas having more galaxies and others having fewer, but as the scale increases, these differences become less pronounced. The CMB, the imprint of the early universe, is pretty homogeneous and isotropic. Let me also remind you that this colorful image actually shows very small temperature fluctuations. If we don't try to represent the temperature with an accuracy of tenths and hundredths of thousandths of a Kelvin, but rather average it to tenths of a Kelvin, then the map of the CMB for the entire sky would look like this: 2.7 Kelvin across the whole sky. It's only when we start being picky and measure the tiniest fractions, then we get this leopard print. And when I say being picky, I mean improving technologies and increasing the sensitivity of observatories. And while everything seems fine with the cosmic microwave background being so homogeneous and isotropic, showing only small fluctuations at the 10,000th and even 100,000th of a degree, there are still anomalies present. The data we obtain from observatories like WMAP and Planck can be analyzed in various ways. I have already talked about some of these anomalies, such as dipole anisotropy and axis of evil, in a separate video. I'll leave a link to it in the description. The presence of anomalies is certainly a problem, because either there's something wrong with our data, or the data is fine and shows a real picture, but what we see is something we completely don't expect, so our current understanding of the universe might be incorrect. Therefore, we need to address these anomalies. Today we're discussing one of the most problematic ones, the cold spot. So what's so anomalous about it? As we've already seen, small temperature fluctuations across the microwave background are quite common. There are many colder spots throughout the sky. What makes the cold spot anomalous is a combination of factors. First of all, the cold spot is, well, cold.
Wow, what a surprise!
The temperature of the cold spot is on average 70 microkelvins lower than the average temperature of the CMB. So it is 0.00007 Kelvin less than 2.7255 Kelvin. So far, it doesn't sound very impressive. In some of the coldest areas, it is colder by 150 kelvins. Overall, it is one of the coldest places in the entire sky. But what truly makes it anomalous is its size. Its diameter is about 10 degrees, and that in the sky is equivalent to 20 diameters of the full moon. Moreover, this cold spot is surrounded by a ring with temperatures above the average. Such a large size truly makes the spot very strange. Typically, noticeable fluctuations in the CMB occur on scales up to 1 degree, but here we have 10. One of the predictions about the properties of the CMB tells us that the deviations should follow a specific pattern. It should follow Gaussian or normal distribution, which can be described by a bell curve. This means that at the peak of the curve, we have the average temperature values, which are the most likely. However, the more significant the deviation, whether to either side of the peak, whether positive or negative in temperature, the lower the chance of encountering such a deviation. Therefore, in the literature and scientific papers about the cold spot, it is frequently referred to as non-Gaussian. This indicates that the chance of such an anomaly occurring with such a deviation and such a size purely by random chance, assuming the universe operates as described by modern theories, is quite low. The chance of this is estimated to be 1% or less, so it is non-zero but still very low. Low enough that instead of attributing it to random chance, we should rather investigate whether something more interesting is happening here. The cold spot was initially discovered during the analysis of data from WMAP Observatory, which studied the microwave background. At that time, it could still be attributed to an artifact in observations or an error in the analysis. But after the more advanced Planck Observatory confirmed the existence of the cold spot, the anomaly became an even more serious problem and a threat to our understanding of the universe. So it is believed that these temperature fluctuations formed during the earliest stages of the universe's existence, when quantum fluctuations were stretched during a brief period of inflation, a very rapid period of the universe's expansion. In my recent video about inflation, I went into detail about this. As a result, these stretched fluctuations led to small variations in density in the early universe. Later on, this difference in density resulted in the formation of structures in the universe, such as galaxy clusters, voids, and so on. These density inhomogeneities were imprinted in the cosmic microwave background radiation at the moment of its emergence, approximately 380,000 years after the beginning of the universe. They were imprinted on the so-called surface of last scattering. But what happened next? Right now, we are detecting photons of the CMB that have been traveling to us for almost the entire existence of the universe, approximately 13.8 billion years. These photons traveled through an expanding universe where structures evolved, galaxies and galaxy clusters formed, collided and merged, chemical diversity increased, and so on. So the picture of the CMB that we observe is a combination of the initial imprint of density inhomogeneities and what happened to the photons afterward. What happened to them can introduce distortions into the picture that we ultimately observe, and various effects can come into play here. Could the cold spot possibly be explained by something like that? When radiation interacts with matter, it can gain or lose energy depending on the situation. The simplest explanation that comes to mind is that the cold spot is just a result of contamination of the signal from something located in our galaxy, for example a cloud of galactic dust or some unusual object. However, observations from various celestial surveys have not found anything like that in that region. There's also the Sunyaev-Zeldovich effect. The essence of this effect is that the photon interacting with matter can lose energy if the energy of that matter is lower, or gain energy if the matter's energy is higher, for example, if it is hot plasma. The effect can have different natures: thermal, related to the temperature of the matter, and kinetic, related to its motion. In general, this also introduces slight distortions in the microwave background. This effect was also attempted to be used to explain the cold spot anomaly, but without success. Now let's move on to one of the main explanations, the supervoid. Speaking of voids, how empty are they? You might have heard the notion that voids are empty regions where there is absolutely nothing. And that is certainly not the case. And I'm not even talking about dark matter and dark energy. The density of ordinary matter, which makes up interstellar gas, stars, planets, and galaxies, is indeed lower in voids. Voids are defined as regions of space where the density of galaxies and matter is less than 30% of the average density of the universe. It can be as low as 1/10 of that average. But that's the average density. When comparing to a galaxy cluster, there can be orders of magnitude fewer galaxies in the void. One of the largest known voids, the Buddhist void, can be 250 to 300 million light-years in diameter, has only a few dozen galaxies known to us so far. There may be more, but that's what has been discovered so far. For comparison, in the Virgo cluster, which is only about 20 million light-years in size, there are thousands of galaxies. In general, voids are indeed very empty. But there are still galaxies there. They're just very few. As for the cold spot, the general idea is that it can be explained by a gigantic void. It suggests that when CMB photons pass through a massive void, they lose energy. So, if along the line of sight from the surface of last scattering to us, the observers on Earth, the photons encounter a void, we will see a decrease in the temperature of the CMB in that direction. And if this void is unusually large, the cold spot will also be very large. The specific properties of the void and its size vary depending on which epoch of the universe we are considering and how far it is from us.
But wait a minute. Some of you might have a question. Why should photons lose energy while traveling through a vast void?
Some might say, well, they travel for a long time, and the universe expands, and the wavelength of photons stretches. And that's true. But the part of the universe where there is more matter expands too, right? Intuitively, one might think that as it passes through an area of the universe where there is more matter, the radiation might lose even more energy, scattering on that matter and transferring energy to it. We already established that when interacting with matter, radiation can both lose and gain energy. However, in this case, the effect is not significant at all. In the case of voids, the story is different. The expansion of the universe plays a key role here. In general, effects such as the Sachs-Wolf effect, especially the integrated one, and Rees-Sciama effects are at play here, but we won't get into the details here. But let's examine how voids can make areas of the CMB colder. First, let's remember that not only matter is subject to the influence of gravity, but also radiation. According to general relativity, mass distorts space-time itself, and photons follow these distorted paths. Next, what we need is a thing called gravitational redshift. The essence of it is that when radiation escapes a gravitational well, it loses energy. A photon cannot move slower in the vacuum, so this manifests as a decrease in frequency and increase in the wavelength of the radiation. In other words, it shifts towards the red part of the spectrum. We can imagine a situation where we have two identical lasers, one located on the surface of the moon, while the other is far from massive bodies, just in open space. Detectors are positioned at equal distances from both lasers. If we measure the wavelength of the lasers, the one shining from the surface of the moon should theoretically have a slightly longer wavelength. Because the laser is inside the gravitational well created by the moon, it loses some energy while escaping from there. In practice, the effect in this specific example would be very small, but it has been confirmed multiple times in laboratory experiments. The reverse is also true. When a photon moves from a region with lower gravitational potential to a region with higher gravitational potential, meaning a photon is effectively falling into a gravitational well, it gains energy. It is subject to gravitational blue shift. And how does all this relate to voids? Compared to the surrounding universe, a void is a region with lower gravitational potential, and in contrast, a cluster of galaxies has a higher gravitational potential. If a photon or electromagnetic wave first travels through a region of the universe with less matter and then enters a cluster of galaxies, it effectively falls into a gravitational well, which we can call a valley. And in this case, the photon gains energy through gravitational blue shift. However, after passing through the entire cluster, when it exits, it will have to escape from the well or valley, and it will lose energy. The situation with a void is the opposite. When a photon enters a void, it has to climb up from the valley to a gravitational hill. As it leaves the cluster, it loses energy. However, when the void ends, the photon rolls down the hill, once again gaining energy. In an imagined, idealized scenario, if we talk about a cluster, we can imagine that a photon loses as much energy when exiting as it gained when entering, resulting in a net change of zero. And the opposite applies to voids. This means that we wouldn't observe any distortions. However, the fact is that we do not live in an idealized scenario.
I noticed that.
And an important factor here is dark energy or the expansion of the universe. If a void or a cluster is enormous, and the photon spans a significant portion of the universe's evolution traveling through it, due to the expansion of the universe, it has time to, expand. The expansion of the universe reduces the density of matter as the volume of space increases, and this means that the gravitational potential also increases. In our analogy, the expansion makes the gravitational valleys shallower and the hills flatter. And now the main point. When the photon first enters a region of increased density, into a cluster, falls into the valley, it gains a certain amount of energy. If the universe were not expanding, it would spend the same amount of energy upon exiting, but the universe has expanded, and upon exiting the valley, the ascent is no longer as steep. To escape from it, the photon has to spend less energy than it gained upon entry, which means it retains some extra energy. As a result of this effect, it has gained energy, and we observe this as a photon with a shorter wavelength and a region of the microwave background with a higher temperature. The only thing is that I show the greater energy of the photon in blue because of the blue shift, while on the map of the CMB, a higher temperature is represented in red. So when we observe a hotter spot, there could be a higher density of galaxies there, and the opposite occurs with the void. As it climbs the hill, it loses energy, and after the expansion of the universe upon exiting the void, the hill is no longer as steep. So, as it rolls down, the photon does not gain back the energy it spent climbing the hill, and it ends up with a net loss. This makes the region of CMB colder, and the process I just described may play a significantly larger role than a change in energy, for example through interactions with matter. Hence the conclusion. If we look at a certain patch of the sky and see a large cold spot, it can be explained by the presence of a massive void in that direction, which has cooled down the CMB in that part of the sky. This is roughly the reason why it is believed that the Iridian supervoid could be there. This enormous void could explain the cold spot, but have any signs of the supervoid been found through other means? If we want to explain the cold spot using the void, we need to ask two questions. First, is there a single supervoid or several supervoids in the direction of the cold spot? And second, can voids really explain such a significant cooling?
And there are scientific studies that try to find answers to both questions.
The cold spot was discovered in 2004. In 2007, a paper was published in which the authors attempted to find a void in the direction of the cold spot. For this, they used the NVSS catalog of radio sources. Among the extragalactic sources in this catalog, there can be radio galaxies and active galactic nuclei. The authors of the study concluded that in the direction of the cold spot, there is a noticeable drop in brightness of radio sources. This means that there could be fewer galaxies there, and therefore a supervoid may be located in that direction. In 2010, as a sort of response to the previous study, another paper was published. Its authors, on the contrary, did not find any statistically significant evidence of the presence of the supervoid in the data from this catalog. In 2014, a paper was published in which scientists described a possible discovery of an unprecedented supervoid that could reach 1.8 billion light-years in diameter. In this case, observations in the visible spectrum from the Pan-STARRS survey and infrared observations from the WISE observatory were used. The authors claimed that the void is located 3 billion light-years away from us, which explains why it was not discovered earlier. In previous attempts to find the supervoid, more distant regions of the universe were studied. By the way, the Eridanus supervoid is named so because the constellation of Eridanus is located in the sky in the direction of the cold spot. But here's the catch. Even if this void from the latest study exists, the authors of that paper note that it still cannot fully explain the drop in temperature observed in the cold spot. Such a void can account for only a drop of 20 microkelvins, and as you remember, we observed an average of 70 microkelvins. That same year, by the way, another study was published in which scientists stated that to explain the cold spot with the supervoid, the void would have to be so enormous and so empty that this alone would break our current models of the universe. As I said before, we're trying to explain one anomaly with another anomaly. But what if it's not just one huge void, but rather a group of smaller separate voids along the line of sight towards the cold spot? This hypothesis has been tested. In 2017, scientists studied data on the redshifts of galaxies and discovered 3 voids, and possibly even the 4th one, in the direction of the cold spot. Each of them was smaller, which somewhat eased the pressure on our cosmological models. and their combined effect on the CMB turned out even greater than that of a single enormous void. However, it was still not enough, only 31 microkelvins. But what's even more interesting is that, to double-check the idea with voids, the authors decided to look how they are distributed in a different direction, and they found a roughly similar distribution of voids. Yet there was no cold spot there. In general, their conclusions were that a supervoid or several voids cannot explain the spot. But the story with the void doesn't end there. In 2021, a major study was published in which scientists created a map of dark matter distribution using data from the Dark Energy Survey and, in combination with other data, discovered the presence of a supervoid at a distance of approximately 2 billion light-years from us. But here, again, the problem is the same. The void may exist, but in its current form, it cannot fully account for the cold spot. The authors of another paper that was published even more recently came to the same conclusion. Known voids in that direction cannot fully explain the cold spot. But if it's not the void, then what is it? There are some quite extreme explanations, such as a so-called texture, a topological defect of the universe. It is believed that in the earliest stages of the universe's existence, when phase transitions could occur, defects could form in the very fabric of spacetime. Monopoles, strings, domain walls, and textures. And according to one version, the cold spot could be a result of the formation of such a texture in the early universe.
Insert a joke about getting stuck in textures.
The problem is that so far we have found no evidence of such defects. There was an idea that the inflation, the period of very rapid expansion of the universe, did not occur uniformly everywhere. However, there is still no solid mechanism explaining how this could have happened. Another interesting idea is that cold spot is the result of the collision of two universes. This requires assuming the existence of parallel universes within a multiverse, and that these bubbles of universes can sometimes collide. Again, this is still just a hypothesis. Of course, a combination of effects is also possible. I already mentioned that there is a chance, albeit small, that such a large region of reduced density could have arisen from quantum fluctuations during the early stages of the universe's existence. It is possible that there's some random deviation there, plus on top of that, there may be a void or several voids. Perhaps there is something else as well. Or maybe it's time to throw our current theories out of the window and acknowledge that we really don't understand anything at all. That might be also too radical of a move. One thing is clear. There's still no definitive explanation for one of the most significant and strange anomalies. And perhaps, in trying to solve that mystery of the cold spot, we will learn something fundamentally new about the universe.
Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye!